Hello everyone, thanks for coming. So today we'll do a brief review of our week 4th lecture for ODE linear differential equations. So in this week, we have learned some applications of the second order ODEs as well as going to the concept of higher order ODEs. So an important application of the second order ODE are the mechanic vibration models. So for those models, we have a mass tied to a string. So the string force will offset gravity, but if we perturb the system a little bit, then the object will start to move. So the equation is mass times the acceleration equals to gravity minus the string force minus the air friction plus the external force, capital F. So if there is no damping, which means the friction is 0, and if there is no external force, we call this free oscillation. So we have the equation mu double prime equals to minus k ut, because when the system is at equilibrium, mg equals to kl. So if the system is damped, which means there is friction, then we do have this friction term, but if there's no external force, then we don't have the last term. So for this case, the vibration will vanish as t goes to infinity because there is no external force and there is friction. Then we go to the chapter of higher order ODEs. First, we study the concept of homogeneous equation. Homogeneous means homogeneous linear equation. Homogeneous means the right hand side is 0, and linear means the equation is linear in y as well as all of y's derivatives. So for this equation, the solution can be expressed, the general solution can be expressed as a linear combination of n linearly independent fundamental set of solutions. Fundamental set of solutions means n solutions whose Wronskian is non-zero, and they are, equivalently speaking, they are linearly independent. Any one cannot be expressed as a linear combination of all other solutions. Conversely, linearly dependent solutions means there exists a set of constants from k1 to kn such that the linear combinations of n, those n functions, is 0 on this interval. Then we studied the non-homogeneous equations. Non-homogeneous equation means we have a right-hand side, and the right-hand side is non-zero. Generally speaking, it is a function of t. Adding two solutions of the non-homogeneous solution is a solution to solve the corresponding homogeneous solution because the differential operator is linear in y. Therefore, the general solution to this non-homogeneous equation could be written as a particular solution plus the general solution to the homogeneous one. So linear differential operator again means if we have a function c1y1 plus c2y2, then L acting on this function equals to c1ly1 plus c2ly2. So what does it mean to have linearly independent set of solutions? For example, 1, t squared, they form a set of linearly independent solutions because Wronskian is a non-zero constant. Finally, for the linear constant coefficient ODEs, we can generally solve them. So the problem looks like this. All the coefficients are constants, and we assume that a0, the coefficient for the highest order derivative, is non-zero. So first, we form the characteristic polynomial. Basically, we replace yn with Rn, yn minus 1 with Rn minus 1. We solve this to find the roots. If the roots are real and distinct, then the general solution could be easily written as a general linear combination of the functions e to the power Ri times t. If the roots are complex, then we just replace those real value functions with e lambda t times cosine mu t, where r equals to lambda plus or minus I mu. So we get some trigonometric functions in this general solution. Finally, if we have repeated roots, then suppose R1 has multiplicity s, then e to the power R1 t e R1 t to t s minus 1 ERT, they are linearly independent and they are all solutions to this ODE. Thanks for listening.